Last year or in O levels?
Last year.
Last year, very good. And what are indicators?
Indicators. So for example, pH indicators, it just shows how like a change. It just shows a change in the reaction.
And do they show the endpoint of a reaction? Indicators are complex organic compounds which
I mean,
show
if like
Hmm?
I was gonna say, yeah, it does show the end reaction, but if you're observing it while you're slowly adding it, you can also see what's happening mid-reaction.
It tells you that the reaction is completed.
Yeah, it does.
Normally, indicators are weak acids. Weak acid means they partially ionize in water, and they reach always an equilibrium, and they have a pH range over which it changes color. Methyl orange, a famous indicator, and then thymol blue, pH is equal to 1 and pH is equal to 4. These are the indicator phenolphthalein, and the phenolphthalein is having this color change. Many indicators are weak acid and partially dissociate in aqueous solution. So
Yeah.
for example, this is an indicator. It dissociates in H plus and IN. IN is a symbolic word. IN represent the indicator negative ion. So you have to copy this screen.
Yeah. Many indicators. Indicators.
Acids are either weak or strong. When we say strong acid, it means it dissociates fully. And when it's a weak acid, it does not dissociate fully, it dissociates partially.
Yeah. So an unionized form is HLN. Wait, what's LN, by the way?
No, it's not Ln, it's In. It's a symbolic word here. It's a
Mhm.
symbol for indicator. In is not a chemistry element. It is used to show an indicator version. So it's In stands for indicator.
Indicator. Okay.
It is the anion of the indicator.
All right.
What is our first concept for today? An indicator is used to show the end point of a titration type reaction. What is our second concept for today? Indicators are generally weak acids and they establish an equilibrium, so we can control the position of the equilibrium. We can shift equilibrium left to right and right to left.
So wait, so the four directions exothermic, H plus and Ln, or IN, or what do you call it?
Ion for indicator. So in acid, increase of H plus, equilibrium will shift to the left. Look at this equation. If I add an acid in titration, either you are adding an acid or you are adding an alkali. So if I add an acid, equilibrium will move to the left. Equilibrium will move to the left. What happens if I add an alkali?
Oh, it's a Chatelier principle. Okay, so an acid increase of H plus, equilibrium moves to the left to give the undissociated form, and alkali increase of OH removes H plus to form water. So equilibrium move to the right to produce a blue color.
So it means that our third concept comes here, that indicators are actually working on the principle of Le-Chatelier. And it's actually moves the equilibrium left to right or right to left. That is how it works. In acidic solution, equilibrium goes to the left. And in alkaline solution, equilibrium shift to the right. IN shows here indicator. Any indicator, because indicator structures are not in our course. So we are just abbreviating it by IN. You have to copy this.
IN. Right.
This is an indicator table which should be partially known, that every indicator has a range, has a threshold pH at which it changes color. All indicators do not work in the same pH range. Look at the methyl orange. Look at the methyl orange and its pH range. Look at the litmus. Look at its range.
Oh, yeah,
Look
68, phenolphthalein, 8 to 10.
Yes.
That's the only range it actually shows the pH change. Is that it?
Yes. So it means different indicators changes their pH.
What about
Res-
11 to 14?
Hmm?
What about
Show,
11?
sorry.
What about 11 to 14?
11 to 14 is the region of high, very high alkaline solution. Normally, we do not refer anything there, phenolphthalein, methyl orange, litmus, but for that range, we have something we call it universal indicator. Have you heard about it?
Universal indicator, yeah.
So that is an indicator which can use for nearly every pH. But as the three famous are here, we generally focus on that. Now you have to give a heading, pH sketches.
pH sketches, all right. Done.
This is a typical titration apparatus, and I want you to recall the concept of titration with me.
Yeah.
By this animation, so we can recall titration.
In a titration experiment, a solution of accurately known concentration, called a standard solution, is gradually added to another solution of unknown concentration until the chemical reaction between the two solutions is complete. Let's consider the titration of an unknown concentration of a hydrochloric acid, HCl, solution with 0.20 molar sodium hydroxide, NaOH. Click on the button to begin the titration. Choose to add NaOH to HCl in 5.00 milliliter increments. Note that hydrogen ions H+ from the acid combine with hydroxide ions OH- from the base to produce water. Also note that as H+ is removed from solution, the pH of the solution increases.
So I'm adding, as you know, this is how titration works. I'm adding 5 units every time. And this is the graph. In the paper, they can ask you to draw the graph. Now, what happens when titration reaches the end point? The pH suddenly rises. Look at this sharp change.
At this point in the titration, the acid has completely reacted with or been neutralized by the base. This point is called the equivalence point. In the titration of a strong acid with a strong base, the pH at the equivalence point is 7. Note that only sodium ions and chloride ions are present in solution. Because these ions will not affect the pH of the solution, the pH is neutral. Click to add more sodium hydroxide. Click to add one final increment of sodium hydroxide. Now let's calculate the molar concentration of the HCl solution. From the amount of base added to reach the equivalence point, you can calculate moles of base. The reaction is hydrochloric acid plus sodium hydroxide producing water and sodium chloride. Or the net ionic equation is hydrogen ions plus hydroxide ions producing water. From the mole ratio in the reaction above, you can calculate moles of HCl. Click on the correct concentration of the HCl solution.
So I think you remember how to calculate. It's a 1:1 ratio. You know the titration volume is 30. You will use the molarity. You need the concentration, get the volume of endpoint, and you know the ratio is 1:1. So then you know the initial molarity of NaOH is 0.2. Putting that, you can find the concentration of HCl. So I save time here and I come back here. This sketch is called the pH sketch. It will be vertical, nearly vertical at a point where titration completes. Okay. So after giving the heading, pH sketches, copy this screen.
Yeah, pH sketches.
Yes, you had given the heading pH sketches. After this, copy this sketch.
Yeah.
The line is vertical when the titration reaches the end point.
All right.
For this end point, we need an indicator.
Okay. Yeah, sketch is done.
Right. In the paper, you might have to sketch it without a rough reading. You need to plot it on a proper graph paper. And this is the convention to follow, that they will give you a proper graph grid and you will plot it in a full way. So the problem was there that how we can locate this point because it is not visible. So this is the neutralization region for every acid, strong or weak, for every alkali, strong or weak. We will get a sketch like that. But the neutralization region will be different. Now we introduce the point here. This is the range for which we need a suitable indicator. You have to update, copy this also on the same diagram. Copy this on the same diagram.
Yeah, I'm coming down. Yeah, done. Sure.
To be useful, an indicator must change over the vertical range. Now, this is the range in which indicator should change the color. Now, I introduce the three indicators: phenolphthalein, litmus, and methyl orange. Right? There are three indicators.
Yeah,
Look
yeah.
at the pH,
I was gonna
methyl
say, but
orange.
like for the bottom one, the very bottom one, and the top one above 8, would that just be universal indicator only?
In our course, there is no range above that, and I will explain you why. Because if you see carefully this sketch, it is starting from an acid. Now, above phenolphthalein, the number is 8. So logically, you can't start the reaction above 8 because logically you are reacting an acid and a base. Every acid will at least be below 7. So whatever you do, the reaction will eventually start from a number less than 7. So let me mark 7 here. So when you mark 7, any acid maximum till here will at least get phenolphthalein.
Phenolphthalein, all right.
Did you get the point?
Yeah, I do get
Actually,
the point.
you will not start from here in any case, because above 7 it's already alkali. So alone alkali is not reacting, it's an acid based reaction. So weaker to weaker acid, you will, for a weaker to weaker acid, you will get a number less than 7. Now for example, I have this case. Now you can see in the vertical range which indicator is working. In the vertical range,
Only
phenolphthalein is
phenolphthalein,
working.
yeah.
So I will select phenolphthalein. Now there are 4 types of acid-base titration. Each has a characteristic curve. Strong acid versus strong base. Weak acid versus strong alkali. Strong acid, weak base. Weak acid, weak base. So how many options are there in these sketches? There are 4 options.
Strong acid. Wait. When it says V, does that mean strong acid with?
Versus. This is I'm sorry, this is a typing formality. Strong acid versus strong base.
But it's basically versus another way of saying strong acid mixed with a strong base.
We are mixing now. We will combine strong acid with strong base.
Yeah.
So we will take acid and base reaction. So now you have to copy this screen.
All right. You're done.
Good. Now I'm starting with, in the following example, alkali is 0.1 molar added to 25 cm cube of acid. Endpoints need to be neutral. So look at this sketch. I think you can see and easily judge, is it a strong acid versus strong base written on the top, but from the sketch, how I can say it's a strong acid versus strong alkali?
Strong acid versus strong alkali. Wait, for strong acid versus, what do you mean? Strong acid versus strong base, then it would have to be a really low pH, right?
Yes, in the start and really very high pH in the end.
Okay, so it would start off with a really low pH and then zoom up to a really high pH.
Right, then?
Yeah.
So it means it's a strong acid versus strong base. Now remember this picture. Huh? Methyl orange, litmus, phenolphthalein. Remember this picture.
Right.
Then can you tell me for this strong acid versus strong alkali, which indicator or which indicators are suitable?
Suitable, all right.
Which one of them, or do you think all of them?
1 and 13. 1 and 13 is when it sort of cuts off.
But line is so straight in a
Why?
big range.
So it's a very sharp pH change. So it was a question.
I want to ask here that in my reaction, I'm getting such a big range of neutralization.
Yeah.
In this range, which indicator or which indicators are suitable?
Okay, can you go back to, or asking for the midpoint, like the convergence in neutralization?
No. I repeat my question. Actually, every indicator is working in a range.
Yeah,
okay?
all the indicators can be used here.
Yes, perfect. So all of them are suitable.
All right. Oh yeah, all of them are suitable.
So you can use in this case, you can use any indicator. Now I am using strong acid, weak base. How I know it's a weak base case?
How do I know wait, what do you mean? Weak base. It's weak base because in the graph, at least, strong acid versus a weak base, it doesn't zoom up as high as a strong base. It just sort of
And
takes off.
it's just
Yeah.
going up to a bit above 12, a bit above 10.
If it was a strong base, it would have gone up to like 14 or 13.
Right. In this range, I show you the indicators. Now, which indicator you think is the best to be used in this case? Out of the three indicators, which indicator is the best?
For this one, methyl orange and litmus would work, right?
Yes, methyl orange is even the best one because within the range of methyl orange, the line is very straight. And even in litmus, line is a slightly bending.
Yeah.
Okay. Now it's a weak acid, strong base.
All right, weak acid, strong base. So strong base, okay, I think I get it. Weak acid, strong, it affects the bottom bit. Strong acid,
Yes.
strong base and weak base affects the top bit.
Yes.
So because it's a strong base, the top bit is zooming up to 14, but since it's a weak acid, it starts off as 4. So phenolphthalein would be the best here.
So we have a better choice, phenolphthalein. Now this acid is a problem. This case is a problem. Weak acid, weak base.
Yeah.
So in this case, actually no indicator suits. Only choice is universal indicator in some cases, but practically no indicator is a good choice. Why?
No. Nothing suitable. Yeah, fair enough, because it's so sharp.
Yes, it is so small portion, so sharp. Now there are some other pH curves also, like we can combine equations, right? A common equation, we can also see the curve going downward. Now a very technical concept is there. Why our graph is always going from low to high? It means, are we adding alkali from the burette?
There's no, wait, what do you mean?
I mean, my graph is starting from low to high. It's going from low to high. It means what I am adding from the burette.
You're adding NaOH.
Yes, it's an alkali. But is it possible that I take alkali in the flask and I add acid from the burette?
No, you're mixing the weak acid and weak base, then you're titrating the NaOH against it.
But you can see this graph. Okay, now look at this graph. Why the graph is now coming down?
Because it's using acid instead of alkali.
Yes. So it means it is possible that the reaction comes down and we can see different reactions which occurs in 2 steps. Now we come to the main topic of this chapter. This is the core topic. Heading is buffer solution.
Yeah.
Give the heading buffer solution.
Yeah.
Let me first forward you a file and we can do few questions before we go towards the terminal topic of this chapter. This is the main topic and it is nearly the end of this big chapter.
Yeah.
I'm sending you a file on WhatsApp. You can let me know once you get the file.
All right. Okay, I'm looking for it now.
I have shared with you.
Yeah.
And Have you opened it?
Yeah.
Questions. 1. The question is about acids and bases. Identify the acid-base conjugate pairs in this reaction.
Yeah.
So the product of, so that the output of acid becomes the conjugate base, and from the base it becomes conjugate acid. Now you have to see the first part, and he is giving us 1 mark to just write under it conjugate pairs in this reaction. Normally the pairs exist on the right side. Normally the pairs, conjugate acid base pair, exists on the right side.
Yeah.
When
Oh, is the acid
ion
base
is
conjugate?
positive,
Yeah.
when an ion is positive, it means it needs electron. It is an electron acceptor. When an ion is negative, it is an electron donor. Lewis theory says that acids are electron donor, negative ions, and bases are electron pairs, electron pair donor, negative ion, and acids are electron pair absorber, positive ion. So you have to identify conjugate acid, conjugate base.
Yeah. Wait, can you like read that answer? I don't really get this.
Do you remember the discussion we made on this topic?
Yeah, but I just need like, wait, can you just write an answer so I can actually remember? But I'm guessing you just said the plus ion was the acceptor, the minus sign was the donor. But what do you mean by
This is the
identify?
main clue. I have just revised it. Something, an ion which is positive is an electron pair acceptor, and it is an acid, conjugate acid. A negative ion has a tendency to give out electron. It's a donor, and it's a conjugate base. This is a hint for you. This is what we had discussed when we made this topic, and you can recall from the notes, but it's better if we discuss orally. Now, can you tell me what is a conjugate base and what is a conjugate acid? Should I repeat again the concept, or you got it?
I think I just want to know what the answer is so I can actually know for 100%.
Okay, you want to, fine. Look at the plus ion, okay? Let me write it. This is plus.
Yeah.
It is an electron acceptor. So
Yeah.
it is a conjugate acid.
So the acceptor will always be an acid and the donor will always be a base.
It's a conjugate.
Yeah. No, so this is only applies for conjugate pairs.
This is actually conjugate word comes when you are already reacting with this thing. So when you react it, it reverses in working. And this is the concept to remember.
But how do you know which is acid and base on the left side? For the right side, I can understand that. But what about the left side?
It is on the left hand side. It's a very tricky question because many people remember that CH3. Technically, if I tell you, but do not get confused, that in our O level we had a concept that some compounds are acid and some compounds are bases, right?
Yeah.
But in A level, you must have read that acidity is also a relative feature. Sometimes, for example, H2SO4 is a well-known acid. HNO3 is a well-known acid. But when two acids react with each other, what will happen? Technically, CH3COOH is an acid and HCOOH is also an acid. But now, who is giving the acid conjugate?
I don't know which one.
Is it giving the acid conjugate?
Wait, would HCOOH be acid mainly because it's smaller than CH3COOH?
No. It is not it's a strength. It's a game of strength. I explained you it's a game of strength. Who is a stronger acid? But we do not need that theory right now. We just need a simple concept. Who is the conjugate acid?
Who is the conjugate acid? I don't.
On the right side.
Yeah, on the right side is CH3COOH.
Okay, now find the sister compound here, and it will be the base.
Oh, okay, I get it. The opposites.
So the concept is very simple. Left side base, right side conjugate acid. Left side acid, right side conjugate base. Look
Yeah.
at the sister compound. And if you think for a second, after looking this question, you will understand the word conjugate.
Conjugate, okay.
They are actually conjugate to each other. So two concepts are there. How you identify right side, who is the acid, who is the base? Positive ion is an electron acceptor. It's a conjugate acid. Conjugate acid, the sister compound on the left side is the conjugate base.
Yeah.
Got it?
Yeah, got it.
Question number 2.
Stay was made by Bronsted Lowry base. Isn't that just a proton acceptor?
Yes. Bronsted-Lowry says it's a proton acceptor.
Oh, no,
And
no,
what-
no. I'm really confused. Isn't the acid the proton acceptor?
No. There are three theories. Arrhenius theory, which is not important to learn.
Okay.
Bronsted-Lowry theory, which is important. I had given you all the theories.
Oh,
Okay?
that's just that theory. What's the third theory where the
The
acid?
name is not important. It's called Lewis theory.
Okay.
In your syllabus, only one theory is by name.
Yeah.
That is why I had texted you the rag sheet, and I want you to look at, because in final O level, when you are in your final year and you are going to appear for the main exam, I always advise people to look at the syllabus, because syllabus is actually the ultimate document. And whenever you look at the syllabus, you can save a lot of confusion. You can get rid of problems like this.
Right.
I want to show you only one thing, because that will help you a lot when you plan your final studies. Look at this is syllabus, huh? Now read the first line. Look at the syllabus. Read the
Know that
first line.
Bronsted acid's a proton donor and the base is okay. So it is a proton acceptor. Yeah.
Acha. Now read the second point.
Know that acid-base reactions involve the transfer of proteins. Yeah, that's true.
Good. And now read the third point.
Be able to identify Bronsted lower conjugate acid-base pairs. Yeah, the acceptor.
Yes, we just did a question.
No, wait, but that conjugate thing, the acceptor was an acid.
No, but that no, you're making us you're facing a small confusion.
Oh.
That was I was explaining in terms of electrons, but it's the same thing. Something is gaining electron is actually able to lose hydrogen.
Yeah.
I tell you, let me show you. I got your confusion. Let me show you the question again. Where is the question? Yes, here it is. Look at this now. I circle, huh? Is it a proton?
Proton.
Hydrogen?
Yeah, that's a proton acceptor. It's just labeled as an acid, but I'm guessing this is in Bronsted.
But look at on the right side. Is it now H2?
Yeah, H2 plus acceptor.
It has gained an hydrogen.
Yeah.
So it's a base.
But it's labeled as an acid.
No. Look at the left side. Left to right. If you move left to right, it's gaining hydrogen.
I get what you mean. Fair enough. Okay.
Actually, now look at this H and travel on this line and come here. Look at this. It has lost hydrogen.
Yeah.
So it is an acid.
Yeah.
So if you apply Bronsted-Lowry theory, something which is losing hydrogen is an acid. Something which is gaining hydrogen is a base.
Yeah.
And what I was explaining, this a very powerful method. Something which is gaining electron, something which is willing to gain electron is an acid. Something which is willing to give out electron, donate electron is a base. These are two theories.
Yeah, okay, but I do get it. It's just reaction to results.
Hmm?
Yeah, I get it though.
So if we summarize now, okay, we make a summary here. This is a substance X. It is gaining electron, and this is a substance Y. It has a tendency to give electron. Now identify who is X, who is Y. Acid is an electron acceptor and base is an electron donor.
All right.
So who will be acid? And it will be a base. This theory is called Lewis theory. Now come here and make a contrast again. Suppose this is P and this is Q. P has a tendency to give out H plus proton and Q has a tendency to gain H plus. Now who is acid, who is base?
Who is acid? Who is base? So acid is the electron donor, right?
No, electron job is over. Now we are talking about proton.
Oh, so acid is a proton acceptor.
Acid is a proton
Donor. Oh, sorry, proton donor.
Look at the line again. So we need to clear this confusion forever. Look at this first line.
Yeah.
Acid is a proton
Donor.
and base is a proton
Acceptor.
Good. Now I ask you again, acid is a proton donor. So what is P?
What is P? Proton donor acid.
H plus. P is giving out proton.
Yeah.
So what is P? Acid or base?
Acid.
Right. And what about base?
Q.
Right. So now this theory, this theory is called Bronsted-Lowry theory. So this is one theory which is very important, and this is the second theory, which is the additional theory. Are you clear about it, or you want to copy it for the future reference?
No, I'm clear about it.
Okay. Then this question is about acid and bases. The ionic product Kw varies with temperature as shown. Temperature and do you remember Kw, ionic product of water?
Proton water. The product of water, temperature.
Kw.
So you just plot Kw against temperature, right?
But do you remember I'm writing the equation for Kw for memory?
Yeah, it's just for water, H over HA, something like that.
Yes. No. H plus into OH. Simple. Concentration of H plus.
All right.
If you allow water to ionize, it will give you two things.
Yeah.
Now, do you remember that?
Yeah.
So he wants us to draw it, and I think if we can leave it for the next class, and you can draw for me, and we can discuss it. Because if we draw in our class, it will take a good amount of time. Now look at this. This question is about acid and bases. The solution of methanoic acid has a concentration 0.240 mole per dm cube and a pH of 2.20. Calculate the value of pKa for methanoic acid. And it's a 3-mark question. So first, should we write down the ionization of this compound?
Right.
Let us ionize it. Acids release H plus. So I have done that. Right?
Right.
He has given me the concentration of HCOOH. It's a weak acid, huh? Methanoic acid is a weak acid. That is why it's talking about pK. Organic acids are generally weak acids.
All right.
So, can you tell me, should I write 0.24 here? Can I write 0.24 here?
So pKa for methanoic acid solution has a concentration 0 and a pH. Yeah, 0.24 there.
But can I write 0.24 on the right side of the equation also?
Yeah.
No. It's a weak
Well,
acid.
oh, fair enough. Yeah, you can do that. But there's no other value given besides the
No,
pH.
but he
Oh,
has
there's
given
the
us the
pH.
pH.
Yeah, fair enough. 2.20 equals minus log H plus.
Minus log.
Oh,
Of-
K pKa or H plus. Yeah. Wait, how do you find the pKa again? What was the formula for that?
It's a log. The letter P means log. But if we work together, can you start working with me? You copy this much also, and I need help, so you can find the
Okay.
H
Anyway,
plus.
K. This is question 4, right?
Yes.
Okay, so the H, yeah, you find 2.210 equals minus log. You divide 2.20. Wait, how do you do that? Minus log 10. Would that be 2.10 to the power of I get it. You find H plus, and that equals to 6.3 times 10 to the power of negative 3.
6.3, 10 power.
Negative 3. To be fair, that's a very simplified version, but yeah. Then at that point, the Ka would be...
Do not jump on Ka. Now,
Yeah.
can you tell me that on the right side, the ratio, is it 1:1?
Yeah.
So if I write 6.3 into 10 power minus 3, can I write the same thing here?
Yeah.
Now, what is Ka? Ka is actually Kc for acids. So can you
Yeah.
help me write the equation for Ka?
Isn't it K equals H plus OH minus over HA?
Oh, that's not K, that's Kw. I'm talking about Ka.
Oh, okay, over HA.
Look, this one.
Oh, I get it. So you do 6 times 10 to the power of negative 3 squared divided by 0.24. You'll get the Ka. Then to find the pKa, you just do minus log the Ka.
Yes, very good. Now you got it.
Yeah.
So now complete it.
Right. Okay. Hello?
Yes.
Hi. So yeah, I'm done.
So did you get the value?
Oh, so the value I got was 3.78.
3.78.
Yeah, that's the
Final
peak.
Okay, good. This question is about acids and bases. Calculate the concentration of hydrogen ions in mole per dm cube in a solution of pH. That looks easy.
dm cubed in solution of pH. Okay, so calculate the concentration with pH. Oh, that's simple. Yeah, 9.4. It'll literally be 10 to the power of negative 9.43. You'll get your answer.
But you have to show steps in the paper, right?
Yeah.
So please share this working and get the answer.
The answer that I got 3.7 times 10 to the power of negative 10.
Calculate the pH of the solution formed when this much mole per dm cube and mix with, we have not practiced this question yet.
Yeah.
We haven't practiced this yet. The pH of two salt solutions are this. Which acids and bases could form the salt in solution J and K? This is an MCQ. Solution J shows a weak acid and solution K shows a average alkali. Solutions are equimolar, 1:1.
Mm-hmm. Hey, what question is this? 7.
Number 7.
Which acid could form the salt in solutions J? Okay, which acid basically form the salt in solution J and K? HCl and NH3 gives you CCO, acid and base forming the salt in solution J. Oh, I get it. Solution J is pH of 5, so it has to be. Wait, when it says solution pH, I'm guessing it means the center point, right?
He says that pH of two salt solution are pH 5 and pH 9. Remember that when you react strong acid and strong alkali, you get a neutral salt. He's not getting a neutral salt. He's getting a salt with 5, getting a salt with pH 9.
Yeah.
HCl, NaOH. I talk about B first, okay? HCl is a strong acid and NaOH is a weak alkali or strong alkali?
Weak, and that's a strong alkali, right?
Good. So if they react, the product will have a pH equal to 7. But J, look at the J pH. J pH is 5. So option B is wrong.
All right.
Now work out option C and D. HCl and NaOH, are they strong acid, strong alkali?
Strong acid, strong alkali.
I'm talking about option C. So when
that's a strong acid, that's a strong alkali, yes.
So pH would be 7 for this case.
Yeah, pH would be 7 for that case.
But what about K? The pH of K is how much?
pH of K is how much?
Look on the question data. Look at the data in the question.
Okay, the answer is A. The answer would be A, right?
But why I should cancel C?
Cancel C because it's strong acid, strong base. pH is 7.
So, but its pH is 9. Now, how I select B and C are cancelled, okay? B and C are cancelled, but how I select between A and D now? HCl is a strong acid, and what about ammonia?
Ammonia, strong acid. Is ammonia a weak acid?
Ammonia is a weak alkali.
Yeah. Wait, what examples of strong alkali?
NaOH, KOH.
Okay.
Acha, ammonia is a weak alkali. Ammonia is a weak alkali. It will not be able, the graph will stop somewhere before 9 or 7 like that. So if you use HCl, strong acid, weak alkali, do you think J can be 5? He has given the pH of J as 5. When they react, if you remember the curve for a weak base, the curve will bend a much earlier position. So if you are reacting with a strong acid with a weak alkali, the pH will be around 5.
Yeah. So no, it just is A. I'm just going through it in my head right now. It has to be A. It just has to be A. I'm just going through in my head.
But why? What about now justification for CH3C? It's a weak acid. What is CH3COOH?
Okay, no. So B and C is crossed out because it's a strong acid. It just doesn't fit in. But
Right.
so for D, so what we want to discuss now is DNA, right? So
I just want to discuss DNA.
Yeah, D. So for D, it's a strong acid, and it's also a strong NH3 is a base, right?
NH3 is a weak base.
Yeah, it's a weak base, but which is for solution K, that can't be right, because if it's a strong acid and a weak base, if it was a strong acid, if it's a strong acid and weak base, it can't have ever reached 9.
Yes, that's the point. You got the point now.
Yeah, so like just like what's called, I'm not sure why A is correct, but just using deduction, it has to be A.
The same rule by which you rejected D will explain why A is the answer. If HCl is a strong acid and ammonia is a weak base, the pH can stop at 5. You remember the curve?
Yeah.
So it can stop at 5. On the second option, CH3COOH is a weak acid and a strong alkali. Can it take it up to 9? This one is a
I can.
weak acid, and this is a strong alkali.
Yeah.
So if I'm using a strong alkali, do you think the graph can reach up to 9?
Yeah.
So 9 is possible. The pH of K, look at the given data, pH is equal to 9.
pH is equal to 9. All right.
This question is about acids and bases. Devise an experiment to determine the acid dissociation constant for a solution of ethanoic acid of unknown concentration. This is a paper 3 question. Assume you have access to a pH meter and a solution of sodium hydroxide of similar concentration to the acid, and include how to determine Ka.
All right.
We haven't done this. It's a laboratory work. This is called core practical. Core practical maybe 9 or maybe 10. It's core practical.
Yeah.
In every chapter, there are sometimes 1 or 2 core practicals. If you scroll the syllabus, you go down, and you see here, look. Look at this core practical. Read this.
Finding the Ka value for weak acid.
Okay. Now you have read the syllabus outcome, and now you read this question. Is it a weak acid?
That's a weak acid, yes.
And what he is willing to ask?
He's asking, yeah, I still have to do weak acid formula.
So can you see it is actually this, he made this question from here.
Yeah.
So that will be a benefit if you get this habit of looking in the syllabus, and then you know that we are not doing this question right now because we haven't done it. I have to share a video for that.
Yeah.
This question is about acid and O buffer solution. Buffer solution we haven't started yet.
Yeah. So is that for, okay.
So we are left with the mixture work. We have to do that work, and equilibrium constant Kc. So let's try this question next time. And we have done work with, we are left with the buffer solution, and we are left with the pH of mixtures.
Yeah.
Okay. So we'll stop here. I will share you this file, and you should, I already have shared with you. So you should try to do some questions from it in till the next class.
Yeah.
Thank you.
Okay, bye.
Bye.